So the types of transformations that we have done so far, we have done translations of functions where they've either moved left and right or they've moved up and down. But we're now going to be looking at stretching of functions. And this is a stretching function that we've got at the top of your page here. And just to quickly point out a few different things that I've got here is I'm starting with the y equals x squared graph, which is this black graph that I've got drawn here. And then this is what I've said is f of x, okay? F of x is x squared. And then I've said that y is equal to 2 lots of f of x. That's the red graph. So if the red graph is y equals 2 f of x, that's actually saying that the equation is y equals 2 x squared. So think about what's happening here. The y coordinate down here, the y coordinate has now changed so that its y coordinate has been multiplied by 2. So what I've shown on the diagram here is that when x is at 1, the y coordinate has gone from 1 to 2, it's doubled. When x is 2, the y coordinate was 4, but it's now doubled up to 8. And when x was 3, the y coordinate was 9, and it's doubled all the way up to 18. And it's the same on the other side here. So this graph, because all the y coordinates have been multiplied by 2, this graph has got a stretch of it going upwards. And the way that I have shown a stretch in the y direction is with these vertical blue arrows. And you'll notice that the blue arrows are no longer the same size as when it was a translation, but the blue arrows are now representing a doubling. So the gap, whatever the y value is here, it is doubling. So you can see that this blue arrow is actually the same as this bit down here, and this bit down here is the same as this bit up here for a doubling that we've got in that particular part. So I've said here, what has happened to the y coordinates when f of x is transformed to 2f of x? The answer is that the y coordinates have multiplied by 2 which makes the graph stretch in a y direction. Or we could say that that stretch is vertically. And I'm going to show you a bit of an animation that will help us to see what's happened with this graph is stretching from the black one to the red one. And when I think of it as a stretching, I kind of think of it as it like pulling apart, like I'm taking my hands and like pulling it upwards. If you have finished writing that, there's some parts of the graph that haven't stretched. I want you to think why that part of the graph hasn't stretched. So which part of the graph hasn't stretched, Ikram? 0. Yeah, when y and x are both equal to 0. When the y value is 0, why hasn't it stretched at all? Because, yeah, 0 times 2 is still 0. So any points where you've got 0 on a graph and you're transforming it by multiplying f of x by something on the outside, what happens is the 0 parts are going to stay the same. They're not going to stretch. So things are only going to be stretching if they are above or below 0. If they're below 0, what would happen to their coordinates? They would multiply by 2, so they would look like they were going further down. Okay? They're just going to go more in the extremes of the vertical direction that I've got there. So I'm just going to quickly show you on Desmos. First of all, I need to put the a on the outside, and I'm just going to quickly change this from -10 to 10. Okay, so at the moment, the graphs are the same, and you can see I put in a cubic here. I did x plus 1, x minus 3, sorry, x plus 1, x plus 3, x minus 1, so you can see the 3 places that it will be crossing. And look what happens. As I make a become bigger, this hump of it here is going to go higher up. This bump down here is going to come lower down. And these arms, these branches, are also going to stretch as well. So let's just see what happens. When I make a become a bit bigger, can you see how the blue graph has become more extreme, but only in a vertical direction? And you should also notice it still has the same intersection points because that is where it's equal to 0, and 0 times 2 is still 0. So as I make A become more extreme, I may need to zoom out a bit so you can see what's happening. It's quite difficult to see what's really going on there, but that red hump has been stretched all the way up into that kind of shape like this. So we've got that kind of pattern of it stretching out like this. What do you think it would look like if A was equal to 0.5? How would you describe what that might look like if A was 0.5? Pardon? It would shrink. Okay, so it would be the same kind of shape, but kind of shrunk down a bit. So let's actually type in that A is 0.5, and you get that this hump up here has halved down to this bit, and this bump down here has halved up to this bit like this. And you'll also see that this red arm is less steep than the, no, it's not less, sorry, the blue arm is less steep than the red arm because it's halved the y values. And it's the same thing in this case here. The blue arm, which is the transformed one, is less steep than the red one because it's halved the values. Any predictions of what's going to happen? We're going to do this later on, but any predictions what would happen if A became negative, what it might look like? Like it's going to flip. Okay, so I'm actually going to just do A. This is what we're going to be doing later on. When A has become negative, the hump that was up here has multiplied by -1, so it's gone all the way down here, and the same with the other bit. So it actually looks like, rather than a stretching, how might we describe that if it's no longer a stretching? A flipping, but flipping is better to say as what Provert said is a reflection, okay? And if you have a reflection, a negative number that is 2, you're going to have a stretching and a reflection. And that's what we'll be building up to, is putting multiple transformations at the same time. But at this stage, we just want to focus on the fact that as we increase A, we're making the values of the y parts become more extreme, and the bits where it's equal to 0 are not going to change. So we're going to have a look now at one that people find a little bit trickier to visualize what's going on. And this time, my two graphs that I've got, the original one is still that y equals f of x, which is x squared. And then this graph is y equals f of 2x. So let me just quickly grab a different color for my pen here. So this is the green graph. This means we're doing y equals, instead of putting x inside this function here, which is x squared, we're putting 2x. So it's going to be 2x all squared like this. And I don't want to think about how we would sketch that because it's a bit difficult with quadratics to visualize this, but I've plotted them both for us. The black one was the original graph, and the green one is the one where it's inside the function. The x inputs have been multiplied by 2. What does it look like has happened to the x coordinates when f of x is transformed to f of 2x? What does it look like has happened to the x coordinate of the black graph when it is transformed to the green graph? Have a look and see if you can spot what you think may have happened for the x coordinates. It looks like the x values have all halved. Okay, so let's just have a look at a few of these points as an example. So this bit down here, the x coordinate is 6, and when it has become the green one, when we've transformed it by replacing the input with 2x, it looks like the input is now 3. And when we have, I don't know, this one over here, where the input is 8, when it transforms, the input then becomes 4. So the x values are halving, which is kind of weird, right? Because when we did it with the y values, they were stretching, and they were just doing whatever we thought was happening. Like on this previous page, when we had the 2 outside, the y values just doubled. This time, when it was inside the bracket, it's to do with the x coordinates, and it's doing the opposite of what we expected. We would have expected the x values to have doubled, but actually the x values have halved. Now, that is kind of in line with the sorts of patterns we saw with translations. When we had with translations, f of x and then afterwards plus a, it just moved up and down in the way that we expected. When we had f of brackets x plus a, it moved left and right, but opposite to how we expected. If it was f of x plus 3, It actually moved 3 in the negative direction. It kind of did the opposite. And this is the same idea of it doing a little bit of the opposite of what you might think. Yeah.
0.5, would it double instead?
Yeah, very good. So actually, the stretching factor that we've got here, because it was a 2x, it halved. So it stretches by a factor of 1 over a. It stretches by a factor of that reciprocal. So what I've written down here, and you've got this on your pages already written, a f of x is a stretch of f of x by a factor of a in the y direction. So when it's on the outside, it is stretching in the y direction, which means in the up and down direction. F of ax is a stretch of f of x by a factor of 1 over a. So like the reciprocal of it in the x direction, meaning left and right. And when I say left and right in this direction, this black graph with these arms like this is stretching, so it is getting closer to the not to the origin, to the y-axis. And again, there's one part that hasn't changed, and it's this bit that's at the centre here. When the x value is 0, well, half of 0 is 0, so that bit's going to remain at exactly the same point. And again, we're going to look at a Desmos demonstration of this to see what's happening here. The reason this is happening is because to get the same y value, you're having to put in half of the x value to get the same y value as before. And you can try it with a table of values to see why this might be happening. That whatever x value you're putting in here, it's the same as the x value that's doubled of it. It's a bit difficult to show that bit, but it's easier to kind of just see the animation of what happens here. So I'm going to go back to this demonstration that we had, and I'm going to change it from f of x, sorry, af of x to f of ax. And we're going to start off with a being equal to 1, if I can just type that as 1, and we'll zoom in a bit. So as a becomes bigger, what's going to look like is happening to the graph? It's going to move in closer with this central line of the y-axis being the bit that's not going to move. I kind of think, have you ever seen those instruments like the accordions that are like, they're kind of like a spring? No, you've never seen these instruments, but basically it's like a spring where the middle bit, the middle bit of this thing is not going to move, and we're like pushing the two sides towards the center. But this middle bit isn't going to move because of it being the center. So I'm going to make a bit bigger, and you'll see what's happening. It's kind of like squashing as it goes into the middle. That's what I mean. There's this instrument that looks like a...
So whenever touches like 0.
No, you would never get it to touch 0. The whole graph wouldn't like squash to it, okay? So there was something that was interesting because when a was 1, it was exactly the same. But when you get something like a as let's do 0.8 if I can. 0.8 as a fraction is 4/5. And we're doing 1 over 4/5. What is 1 over 4/5, or the reciprocal of 4/5? 5 over 4. So when you have the a is 0.8, instead of it going compressed, it is stretching outwards by a factor of 5 over 4, which is 1.25. So the x-coordinates have now been multiplied by 1.25. If this is 1 here, this coordinate is 1.25. So it's stretched out. And I'm now going to make it, I think Provat answered this already, so I don't want him to answer this. If I made a 0.5, what do we think will be happening to the graph? The x-coordinates will double. The y-coordinates won't change. So I'm going to see if I can make it 0.5. And you can see how the blue graph looks like it's stretched outwards now. Now remind ourselves of these coordinates. They were -3. Well, the new one of that one is going to be -6, okay?
So when it changes horizontally, the y-intercepts stay the same, and when it goes horizontally, then the x-axis stays the same.
Yes, I think what you said is right. In this case, the things that are changing are the x-coordinates because it's an x stretch. On the other one, the things that were changing were the y-coordinates because it was a y stretch. So that's why, when you did enlargements in GCSE, you stretched both the x and the y at the same time. This time we're just isolating. We're doing x's together and then y's separately. So just going back to these coordinates, we said that it went from -3 to -6. This one, which was -1, has gone to -2. This one, which was at 1, has now become at 2. I know there's a lot of coordinates on the board there, but you can just see them as the numbers as well. Now, I am going to think about what happens. Look at how that stretches when A is 0.2.
Okay, so zoom out.
Yeah, let's zoom out. If it's 0.2, what's actually the stretch factor, do you think? Timesing it by 5. Okay, so it is now 5 times wider than it was before because the inside bit is 0.2 and the reciprocal of 0.2 is 5. If I make it 0.1, it's going to be 10 times stretched out. So it's the same graph, but just 10 times wider. Notice the bump at the top, the y-coordinate is 3.079, the y-coordinate is 3.079. Nothing has changed about the y-coordinates, just the x-coordinates are the things that have shifted here. Now, if A becomes negative, what do you think is going to happen? If it's 0, then you're just saying it becomes a flat graph, because you're just saying the graph is just A is 0. Yeah. So that kind of looks a bit weird actually, but let's not think about the 0. What about how if we think it's going to be, what do you think the graph will look like if A becomes a negative number?
Reflect.
There's going to be some kind of reflection. In what line? Let's make A -1. So it's reflected in the y-axis. In other words, it has. I know reflecting is the posher way of saying it, but it has flipped in the x direction. It's still going left to right as a flipping. So the stretching is left and right. The flipping is left and right. The previous example we did, the stretching was up and down. The flipping was up and down. It all kind of matches together here. So we're going to try and apply this to some examples now that we've got stretches as well as translations that we've got here. So I have a curve here, and the curve below is y equals sine x. We're going to do loads more on these graphs when we get to them later on in pure maths in year 1. And we're going to sketch y equals 2 sine of x. So what I'm going to do is I'm going to say let y equal f of x, and we want to sketch 2 sine x. So 2 sine x is equal to what? Now, hang on, maybe I should have said, I'm going to just slightly rephrase that. I'm going to say let sine x equal f of x. So what would 2 sine x be equal to? 2f of x. Now, 2f of x, we know, is a stretch, a vertical stretch. So we could either say a vertical stretch, or we could say a stretch in the y direction. And we could say scale factor 2. So it's either a vertical stretch or a stretch in the y direction of scale factor 2. So all you need to concentrate on is the y coordinates. All you need to concentrate on is the y coordinates. So, the easiest ones are to think about where there's 0, because we just said before, when it's 0, it's going to stay at 0. So I know it's going to stay here, I know it's going to stay here, I know it's going to stay here. And then the next easiest ones are to look at the tops of the bumps. The top of the bump here is at 1, so it's going to go all the way up to 2. This bump goes down to -1, so it's going to go all the way down to -2. If you want to, you could see at this point here it's at a half. So at this point here, it's going to be at 1. This is where it's at a half. So here it's going to be at 1. I'm going in a lot of detail here. You wouldn't need to go into this much detail. I'm doing this for the first one. You really only need the peaks and the troughs. But I'm adding in these extra bits to show you really what's happening. Here the coordinate is -1/2, so it's going to come all the way down to -1. Here the coordinate is -1/2, so it's going to come all the way down to -1. I've doubled all of the coordinates. Now my only job left to do is to sketch those together a bit like a dot to dot, but we try and sketch them as where possible with one smooth line. We never like doing sketches like that. That's awful, okay? We like to do sketches, not like in art. We're just going to try and do a nice smooth sketch. I've missed one, but it's not the end of the world because it's a sketch. It's not about being completely accurate. But I've roughly drawn now what y equals sine x. If I was going to draw this again, my improvements to myself is I'd try and like that bit. I'd also probably like that bit to be a little bit smoother, okay?
So should we draw that?
Yeah, try and draw that one on your graph now. So I've done my first go. I've done an extra bit with my blue bit there to try and smooth it out. It's usually a bit easier to do this. That's a really good one, actually. It's usually a bit easier to do this when it's smaller. I did that extra blue bit because I wanted it to be a little bit smoother.
It's okay. So you just need to sketch it. Doesn't need to be.
It's a sketch, yeah. It doesn't need to be perfect. If you finish sketching it, try and think about, like, why might we even care about this? Who do you think might be using this in their jobs? Who do you think might be thinking this is actually something that's important?
People who look at earthquakes.
People who look at earthquakes, because it looks like this might be something about, like, waves that might be modeling something.
That is so bad.
You've all done physics at GCSE. And waves are to do with sound, okay? Now, what do you think would be happening if this were a sound? Anyone remember from GCSE? If you had made the sound stretched up like that and that, do you know what that might be? The frequency would be the same.
Light waves.
We can't just say random things,
Light
guys.
waves are transverse. Sound waves are longer.
The sounds are what, sorry?
They're the straight ones. Transverse are light waves. So these ones.
Okay.
I do physics A.
That would be one wavelength.
Okay, all I was trying to say is... All I was trying to say is this red wave, I think, from my physics, it sounds louder than the wave below it because it has a higher amplitude. Okay? That's what I was trying to pick out something about these graphs. And you all just started shouting transverse waves, light waves, like all kinds of things. I don't even know what was going on. So all I did was I concentrated on the y coordinates. I didn't change any of the x coordinates. Everything was in an up and down direction. The way I knew that is the value was on the outside of the function.
Where would it be both? As in x and y coordinates?
If it was changing both of them, you might have had something like 2f of 3x, which I don't know if you do in year 1. You do that kind of thing in year 2, but we're not going to think about that just yet, okay? So we're going to try some more examples on this. I'm going to go on to the next page now. So we've got 2 examples here. And first of all, it wants us to sketch y equals x squared x minus 4. Then on the same axes, sketch this other graph, okay? Well, before we even do that, I want you to try and think, how are these 2 graphs related to each other? If I call this one f of x, if f of x is x squared x minus 4, what is this one? What is 2x squared 2x minus 4? How has it changed from this to this? What's times by 2? We need to be specific here. What's been multiplied? The x's have been multiplied by 2. In other words, the x has been multiplied by 2. If I put the 2 outside the front, if I did 2f of x, what would 2f of x actually look like?
It's just that.
It's 2x squared.
There's another one.
It would just be 2x squared
X minus 4.
x minus 4. It's just the whole thing multiplied by 2. So it's not 2 on the outside, it's 2 on the inside, okay? I'm going to put a line through that so we know it's not that one. And if it's inside the bracket, we now know that it is a stretch left and right horizontally in the x direction. So it is going to be a stretch horizontally. Or I might say in the x direction. Or I might just mean left and right. And the scale factor is a half, because it's 1 divided by the 2 that we've got there. And so we are going to concentrate this time on the x or the y. What type of coordinates? X coordinates.
Sean was isolating or something?
Yeah, she's doing a live lesson at the moment, but she's probably back in this week.
The teacher stay over doing a live lesson.
Sorry?
It's have to be a different teacher in the classroom.
Yeah, there's another teacher in the classroom as well, just to make sure everything's working. Okay, so we've now got those bits written down, that it's going to be a horizontal stretch with a scale factor of 1/2. Remember, it's going to look like, we called it a stretch, but actually if the scale factor is 1/2, it's going to look like everything is squashing in towards the middle. So we're just going to concentrate on the x coordinates. I'm going to begin by drawing x squared x minus 4. It's a positive cubic with a repeated root at 0 and crossing at 4. So there's my repeated root, there's my 4. So it's going to be this kind of shape, like this. That should have touched at the top, but it didn't quite. This is my f of x, and then I'm going to use, I don't know, a red colour. All you need to do is concentrate on the x coordinates and half the ones that you know about. Half of 0 is 0. So it is still going to have a repeated root at 0. But instead of it crossing at 4, it's going to cross at 2. So we're just going to draw that same graph again, but you're also going to make sure everything is kind of like halved a bit. So it's going to be like, so there's a few things I have tried to do, and I'm going to highlight these things. I have made sure that the minimum points have got the same y coordinate. I didn't want to affect the y coordinates. I only wanted to affect the x coordinates. I have gone from a 4 to a 2 because I've halved them. And I've generally still got the same shape. It looks like the whole graph has squashed, but this was the middle part of the squashing that happened. Okay? And so this one, we're going to have a look at now as well together. Everyone mostly got that one drawn? So this time we have y equals x plus 1, x minus 2. And they want us to sketch y equals f of x and y equals f of x over 3. Now, they haven't asked us to write down what f of x over 3 is, but sometimes the exercises do that. F of x over 3 would be, instead of there being an x, it would be x over 3 plus 1, and it would be x over 3 minus 2. That's actually what we're going to be sketching. We've replaced the input values. Instead of them being with x, we've replaced them with x over 3. And now I'm going to think about what this will look like as a transformation. So Lily, what do you think this is going to represent? What kind of stretching or transformation would this be? Yep. Good. It's a factor of the reciprocal of 1/3. So it's a stretch horizontally, and it is going to be a scale factor of 1 over 1/3, or the reciprocal of 1/3. The scale factor is a 3. So it's in the x direction, and we're going to concentrate again on the x coordinates. And then we're just going to go for it. We're just going to sketch. So it's a quadratic that crosses at 2 and minus 1. So there's my 2. And there's my minus 1. You'll notice I've drawn these quite close to the middle. Why have I drawn these as quite close to the middle this time? Because I'm going to be stretching it by a scale factor of 3. So I need to make sure I've got room to do the stretching in a second. So I'm going to draw my quadratic. Don't put the bump of your quadratic on the axis. Why? Because it's not on the axis. We know it's not on the axis. If this is minus 1, and this is 2, where is the bump going to be?
Just to the right.
Just to the right. At what value of x?
1.
Nope.
So 0.5.
0.5. The midpoint of minus 1 and 2 is actually 0.5. So you don't have to do this, and I'm going to get rid of it in a second, but that bump is symmetrical about 0.5 because quadratics, they're called parabolas, quadratics are symmetrical. So if they're crossing here and here, we know that that bump is going to be at 0.5. So the bump definitely was not on the axis. And now I'm going to do the next bit. Just going to get rid of that dotted line. We're going to concentrate on the x-coordinates. So instead of it being at 2, it's going to be all the way over here at 6. And instead of it being at minus 1, it's going to be it's minus 1, minus 2, minus 3, roughly. It's going to be over here like this. And make sure it is also going to cross at that point. So it's going to be a much wider quadratic. Now, ideally, I would have liked that 0.5 to have gone to 1.5. So actually, it kind of has done, actually. Can you see how that minimum point, the x-coordinate, is at 1.5? Because the minimum point of this one was at 0.5, and so it's stretched. I'm sorry, that's what you were saying just now, wasn't it? You said 1.5, and I was like, what's he saying? And now I've realized you were thinking about where the minimum point is going to be. So the bump is definitely not on the axis. The point where it crosses the x-axis the y-axis has stayed in the same place. And we could actually work out what that value is. I think that value is going to be when x is 0, it's just minus 2. I should have, though, my bumps ideally should have had the same y-coordinate. This red bump shouldn't look any lower. They should be the same. Is that a question? Pardon?
I got to go to Kerry. Got a meeting.
Okay.
Yeah.
Do you have a note for it?
No, but it's every Tuesday in session 3.
Okay. Well, I'm going to try, because it can't happen every Tuesday. It's going to always be then in lessons.
Sorry?
I'll speak to you about it afterwards, okay? So has everyone got those drawn? So although it's not super obvious, the bumps should be at the same level because the y-coordinates shouldn't have changed. The only thing that should be changing in here is the x-coordinates that we've got. So if you turn over the next page, oh, the next page is actually reflections of functions. So we can have a go at the reflections. Is that when we've got the next exercise? Okay, we're going to stop at this point.